Hi, everyone. Hope you guys are doing well. It is Tuesday afternoon, and today we are talking about lesson 9.4, day 2, factoring to solve quadratic equations. And these are your Ed Puzzle notes for tonight. So, a few things that we are going to touch base upon for today is that our objective for tonight's video and today's lesson is to solve quadratic equations by factoring. Okay. It is the idea that we can solve some quadratic equations, including equations where that b value is equal or not equal to 0, by using the zero product property. And the zero product property tells us that for any real numbers, a and b, if we multiply a and b, we get 0. So therefore, a could be equal to 0. Or b could be equal to 0. Because remember that rule, when you're multiplying values, anything multiplied by 0 is going to give you that value of 0. So 4 times 0 is 0, 2 times 0 is 0, 0 times 0 is 0. So therefore, that zero product property does give us the information to use that if one of the factors is set equal to 0, or if both of them are, then we can have the whole equation be set equal to 0 in order to solve by factoring. So first off, for questions 1 and 2, it's asking us to factor and then use the zero product property to solve each quadratic equation. So the first thing that we need to do is we need to find two numbers that multiply to negative 14 and add to negative 5. So if we wanted to, we could create some factor charts down below. We can add to negative 5 and we can multiply to negative 14, okay? Numbers that multiply to negative 14 remind me of 7 and 2. Well, if 7 and 2 want to add to become negative 5, the 7 is going to have to be negative and the 2 is going to have to be positive. Negative 7 plus 2 does give us negative 5. So therefore, we have the factor of m minus 7 times the factor of m plus 2. And don't forget, this whole problem is still being set equal to 0. So zero product property tells us that this whole factor could be equal to 0. And the other whole factor could be equal to 0. In order to have both of them multiply to get a value of 0. So therefore, we can add 7 to both sides. We get that m is equal to 7. We can subtract 2 from both sides, and we get that m is equal to negative 2. Okay, and there is our first example problem. Now, same thing with number 2. We have to make sure that our equation is set equal to 0, which it is. Our whole objective is to have two factors that multiply to each other that equal 0. And right now we're looking for two numbers that multiply to negative 20 and add to positive 1. Okay, well, when we think of negative 20, we can think of 10 and 2. Negative 10 times positive 2 gives us negative 20, but negative 10 plus 2 gives us negative 8, so that won't work, okay? What about 5 and 4? Let's see. There's a difference of 1, okay, and we want to add to 1, so maybe we're getting closer. We want it to be negative, so maybe 5 times negative 4 gives us negative 20. Okay, that works. And 5 plus negative 4 gives us negative 1, so boom, that works as well. P plus 5, P minus 4. Okay, well, we know that if we're multiplying both of these and we get a value of 0, that either P plus 5 has to be 0 or P minus 4 has to be 0. Now, they both could be 0 or just one of them could be 0, right? So we're going to go ahead and set both of these equal to 0, and then we're going to solve. Okay, we can subtract 5 from both sides. we get that p is equal to -5. And we can add 4 to both sides. And we get that p is equal to +4. And voila, we have factored, and then we have used the zero product property, or ZPP, to solve each quadratic equation. Okay? Now, for example problems 3, 4, 5, and 6, it's asking us to write the equation in standard form, factor, and then use the zero product property to solve. Now, remember, standard form, ax squared plus bx plus c, okay? And we always want to make sure that it's equal to 0 in order for us to use the zero product property. So in this case, question number 3 is good to go. There's really not much that we need to do. So our whole objective is going to be to figure out two numbers that multiply to -15 that add to +2. Now, when we think of 15, instantly I think of 3 and 5. Okay, you can use 15 and 1, but really 3 and 5 is the first thing that comes to our mind. Well, 3 times 5 is 15, but 3 plus 5 is equal to 8, and we don't want that. Well, if 15 has to be negative, 3 times -5 is equal to -15, but 3 plus -5 is equal to -2. And our 2 is positive, so that one didn't work. But let's see if we can flip-flop it. -3 times 5 is -15, and -3 plus 5 is +2, and boom, that one works. So our factors are going to be a minus 3 times a plus 5 is equal to 0. Now, again, with the zero product property, this factor could be equal to 0, or this factor could be equal to 0. So therefore, we're going to set both of them equal to 0 and solve. A minus 3 is equal to 0, and a plus 5 is equal to 0. We can go ahead and add 3 to both sides, and we get that a is equal to 3. And then we can go ahead and subtract 5 from both sides, and we get that a is equal to -5. Now, for example problem number 4, we have 48 is equal to -4x squared plus 4x. Well, we know that if we want it in standard form, this c value is actually going to have to go right in place right there. So we're actually going to subtract 48 from both sides. Okay, when we do so, we get the new equation of 0 is equal to 4x squared plus 4x minus 48. And now that we have that, we can go ahead and see that it's in standard form, and we can go ahead and factor and use that zero product property since it's equal to 0 to solve. Now, before we factor it though, something that really sticks out is that they all share a number in common, and that is the number 4. We can actually factor out this GCF of 4. When we do so, we're left with x squared plus x minus 12. 48 divided by 4 is 12. Okay? Now, in order to factor, we are looking for two numbers that multiply to -12 and add to +1. Well, we know that 4 and 3 make 12, and we know that 4 and 3 have a difference of 1. So 0 is equal to 4 times x plus 4 times x minus 3. Okay? Now, when we have this GCF out in front, a lot of us want to use our natural instinct and just set it equal to 0 as well. But let's keep in mind, when we're setting each factor equal to 0, there's no way that 4 could ever be equal to 0. That's not true. 4 can only be equal to 4. So the only thing that we're actually going to set equal to is just this x plus 4 and this x minus 3. We're going to go ahead and subtract 4 from both sides. We're left with x is equal to -4. We're going to go ahead and add 3 to both sides, and we're left with x is equal to +3. Okay, this 4 out in front, it is the GCF, but there really is not a whole lot we can do with it because we cannot set it equal to 0 and solve for anything. 4 can only be equal to 4, and therefore we just leave it there. Okay. Question number 5 is kind of the same idea where we need that this -49 to be equal to 0. Well, if we have -49 and we need it to 0 out, we're going to add 49 to it. But just like what we've always done is whatever we do to one side, we have to do to the other. So therefore, we're going to add 49 to both sides. Now remember, 49 does not go with 14x. Quadratic, linear, constant. So they do not add together. So really, our new equation is x squared plus 14x plus 49 is equal to 0. Okay, well, zero product property states that we need two factors that multiply to each other, that multiply and become 0. So we're looking for two numbers that multiply to 49 and add to 14. And that is just going to be 7 and 7. Okay, when we set them both equal to 0, they both are the same factor. So what we're going to notice is that we should get the same solution, right? We'll subtract 7 from both sides. We get that x is equal to -7. We'll subtract 7 from both sides, and we'll get that x is equal to -7. And right here, you don't have to write them twice if you don't want to. Visually, what's happening here is if we only have one x-intercept, that is going to be in the same exact position as the vertex. One x-intercept means that that vertex is hitting where x is -7. And so there are no two x-intercepts. There's just one solution because they both land on the exact same spot. All right, and then question number 6 looks a little bit different because what we're going to notice is there is no b value, right? So 9b squared is equal to 16. Now, we could solve this by square roots. We totally could. We could try and divide both sides by 9. We could take the square root of b to undo b squared, but we're factoring here, and we're using the zero product property. So let's go ahead and let's subtract 16 from both sides. And let's create this new equation in standard form of 9b squared minus 16 is equal to 0. Okay, now 9 and 16, they don't have anything in common, not a 3, not a 4. So unfortunately, there's not a whole lot we can factor out of them in terms of GCF. But what we know about 9 is that 9 is that perfect square. 3 times 3 gives us 9. So when we think about breaking this up into factors, we know that we can distribute the 3 and the 3 to make 9. 3 times 3 is 9. Now, what we practiced when we were factoring back in chapter 8 in first semester is that b squared is also a perfect square. B times b gives us b squared. So we can go ahead and we can distribute that as well. Now, 16, again, I think you guys are starting to see that pattern. 16 is also a perfect square, okay? It breaks up into 4 and 4. But here is our catch. This is how there becomes no b value, right? Like this really is 9b squared plus 0x minus 16 is equal to 0. So we really have to think, okay, what are two numbers that multiply to 16, -16, but add to 0? And that is going to be that opposite sign of the perfect square, that difference of two perfect squares. So here we have 3b plus 4 times 3b minus 4, and they're both equal to 0. So because of that, we can go ahead and then set them each individually equal to 0. And we can go ahead and solve. We can subtract 4 from both sides. Oops, my pencil keeps breaking today. We get that 3b is equal to -4. We can divide both sides by by 3. And we get that b is equal to -4/3. Okay. We can add 4 to both sides. We get that 3b is equal to +4. We can go ahead and divide by 3 on both sides. And we get that b is equal to 4/3. And that is the other solution. So sometimes we will still see these difference of 2 perfect squares in some of our problems. Okay. Now, let's finish off these notes for today talking about x-intercepts. Okay. Well, let's remind ourselves, our x-intercepts are the same as our solutions. They're the same as our roots. Okay. And really we're just solving for x. Now, the one key difference is that x-intercepts need to be written as ordered pairs. X, 0, right? An x-intercept is where your parabola is crossing the x-axis, where the y value is 0. So once we solve for x, we're not really doing anything different. Once we solve for x, we're going to want to put our final answers in as ordered pairs. So let's give it a go around. Okay, here we have y is equal to x squared minus 12x plus 35. Okay, well, our whole job is to figure out what are 2 numbers that multiply to 35 and add to -12. Okay. Well, let's see, 35. I like 7 and 5. So 7 and 5 give us positive 35, but 7 and 5 give us positive 12. We don't want positive 12. We want -12. So maybe we'll make -7 plus -5, and that gives us -12. Okay, that works. And -7 times -5 gives us positive 35. So boom, that works. Love it. So in order to find the x-intercepts, we need to set our equation equal to 0, right? Because we're technically still solving. So 0 is equal to x minus 7 times x minus 5. Okay, we can go ahead and set each equal to 0. Okay, when we do so, we can add 7 to both sides. We get that x is equal to positive 7. We can add 5 to both sides, and we get that x is equal to positive 5. But remember what we said. In order for us to solve and to find the x-intercepts, we need to write them as ordered pairs. Remember, your parabola has x-intercepts where it is crossing the x-axis where y is 0. So for instance, this is just like a really rough sketch, you guys. Nothing about this is very accurate. But if we have solutions at 7, okay, here's 7 and 5, okay, what this means is that your parabola is sitting somewhere, it's crossing through the x-axis, and it's sitting somewhere like this, okay? So what are these 2 x-intercepts? Well, that's the point of 7, 0 and 5, 0. Those are the x-intercepts. All right, and then last but not least, for number 8, we have the equation y equals x squared plus 7x plus 12, okay? And 2 numbers that multiply to 12 and add to 7 are, I was going to put the 3 first, I'm sorry, guys, x plus 3 times x plus 4, okay? 3 times 4 is 12, 3 plus 4 is 7. And remember, if we're solving, we want to make sure that this equation is set equal to 0. Now, when we put this in our graphing calculator and look at it visually, yeah, sure, leave it as equal to y. But when we're solving, we want it to be set equal to 0 because that's what the y value is at the x-intercept. Your y value is 0. So we can go ahead and say x plus 3 is equal to 0 and x plus 4 is equal to 0. Subtract 3 from both sides. We get x is equal to negative 3. Subtract 4 from both sides, and we get that x is equal to negative 4. Well, we're not done because technically, as x-intercepts, our solutions have to be written as ordered pairs. Negative 4, 0, and negative 3, 0. Oops, sorry, I think my face is in the way. So objectives for today. I'll zoom out a little bit so you can kind of see everything. Zero product property, solving by factoring. Your equation has to be set equal to 0 in order for the zero product property to hold true. Okay? Once you factor, you can then set each factor equal to 0 and begin to solve. When you're trying to find the x-intercepts, okay, you have to make sure that even though your equation is equal to y, that you are setting your equation equal to 0 in order to solve first. And then your very last step as x-intercepts is to go back and write them as ordered pairs. Now remember, your x-intercept is always going to be the x value where y is 0, where your parabola is crossing the x-axis, and that x-axis does have that y value of 0. So we hope you enjoyed tonight's Ed Puzzle. We'll keep practicing this in class. You guys are doing a really great job, and we will see you guys later. Have a good night. Bye-bye.